Resonance in nonlinear oscillators. Consider the following driven oscillator written with the left-hand side, which looks familiar, x double dot 2 beta x dot plus omega naught squared x, the natural frequency squared. On the right-hand side, we'll have driving force A cosine gamma t, but we will also include the nonlinear force minus lambda x to the third power. This equation has a name, which, as you can imagine, means that this is a non-trivial equation with interesting physics in it. It's known as Duffing equation. And we're interested in exploring resonance behavior of this equation. Turns out there are other regimes that exist for this equation. We seek for solution in the usual form, where x will be given by some amplitude b times cosine gamma t plus delta. Frequency gamma we will write as being close to natural frequency omega naught plus some small detuning. Both epsilon and damping beta will be much less than omega naught. For small amplitudes, we expect that the nonlinear term lambda x to the third power will not matter. So we expect to recover the solution of the old result for simple damped oscillator. This old result says that amplitude B will be related to the driving force amplitude A divided by 2 omega naught multiplied by square root of epsilon squared plus damping coefficient squared. And that the phase shift will be given by the following equation. Tangent of delta is equal to beta divided by detuning epsilon. So this is our old result. What's going to happen as we increase amplitude of the driving force? Let's rewrite this equation in slightly different form that relates amplitude B to the driving force amplitude A. We'll write it as B squared epsilon squared plus beta squared equal to A squared divided by 4 omega naught squared. Previously we found that nonlinear oscillator, in particular quadratic term, the shift in frequency, and the amplitude of oscillations is now given by B, so it's going to be proportional to B squared, is given by 3 lambda, the coefficient of nonlinearity, divided by 8 omega naught. We can call this coefficient in front of B squared as K, and that allows us to modify the equation above and write it as B squared. For epsilon, we're going to change it as epsilon minus the shift kb squared, that shift that we just wrote, and we square that, plus beta squared, and the right hand side remains the same, a squared divided by 4 omega naught squared, which we can rewrite in terms of epsilon, solve for epsilon, and we will have kb squared plus minus square root of coefficient a divided by 2 omega naught b, all of it squared, minus beta squared. Note that we obtained equation which happens to be cubic in b squared. Real roots of this equation will give us the amplitude of oscillations. What will resonance look like? We can consider several cases. First case that we will consider is case of small amplitudes. When A is small, in which case B will behave the same as in the regular damped driven oscillator. So we expect to see B, the amplitude, as a function of detuning epsilon, to be given by the familiar bell curve. However, as amplitude of the driving force increases, we expect that the resonance frequency will start to shift in accordance with the equation that we wrote above, kb squared. And if k happens to be greater than 0, which is the same as lambda greater than 0, then we expect to see that the curve for the resonance will be shifting to the right, to higher frequencies. Second case that we can consider will be an intermediate case, when A is equal to some critical value, A sub c, such that the resonant curve of B versus epsilon will have an infinite derivative at some detuning epsilon, meaning that derivative of dB with respect to d epsilon will be infinite. So this intermediate case will delineate between two cases. Case where we have unique value of B for each epsilon, with the third case where solution is no longer unique. So case 3 will be the case of large driving force, when A will be greater than the critical value of A, large driving force. In this case, we expect to see the resonant curve that looks something like this. There will exist a region where B is no longer a unique value for each epsilon. So the resonant curve, say A, B, C, D, E, and then F, can experience hysteresis. For example, as the frequency of the driving force is being swept, you will discover that the motion along the resonant curve will go through points A, B to C, then it will jump down to E, and then will continue going towards F. When sweeping frequencies down, on the other hand, we would see going through F, then through point D, then going up to point B, and then going down to point A. This region here will be the unstable portion of the resonance curve, which will generally depend on the history of the frequency epsilon. Finally, it should be noted that physics of driven nonlinear oscillator is not exhausted by this interesting resonance behavior. Other physics contained in Duffing equation includes with nonlinear oscillators, there exists possibility for other resonances that will occur at frequencies that are related to natural frequency omega naught by two integers p and q. The strength of these resonances will favor small integers p and q, smallest being p equals 1 and q equals 1. Another behavior that is included in Duffing equation is chaotic behavior that occurs for certain choice of parameters. And we will be studying chaos in the remainder of this course.